So we're very happy to have Andrew here. Tell us about branes, fermions, and superspace.
Okay, well, let me start by thanking you, John and Cody, for organizing this seminar series. It's really great that, well, at least we can see each other virtually and we keep the community together. So, well, thank you. So yeah, today I'll be talking about branes, fermions, and superspace. So this is work in progress that we're doing with some people in Liverpool. So Jamie Rogers and Flavio Tonioni, these are two great students. And Radu Tatar is also involved in the project. So, well, let's start with the outline. So I'll first start giving some motivation for what I'm going to do afterwards. Afterwards, I'll move on to tell you about branes and superspace. I'll provide afterwards a superspace approach, geometric approach to obtain, well, the theta expansion of the brane actions. And once I have the approach, I'll apply it on the M2 brane action, and then I'll move to do, well, dimensional reduction and T-duality in order to obtain the fermionic terms in the different Dp-brane actions. So in general, I mean, this topic, it involves like huge computations, and well, I'm going to skip many computations. Well, mostly I'm not going to give any computation, but I'm going to focus on the physics and the whole approach just to, well, make it simple. So let's get started. Well, the motivation, I mean, on the back of my mind, what motivated me to do this project is KKLT and understanding KKLT from the dimensional perspective. And as many of you know, well, 3 years ago, there was this discussion about perfect squares arising in theories with K-Geno condensates, well, supergravity theories with K-Geno condensates, and so on and so forth. And well, let me just be very rough. I don't want to enter the details, but this led to some speculation, for example, when it comes to fermion terms in brane actions. So what I wanted to see if there's any possibility of saying something like, you know, from first principle, and the answer is yes. So that's what I'm going to do today. So the goal of the talk is going to be basically to talk about, well, the fermion expansion in the different brane actions. And the talk is going to be completely general physics. So it has nothing to do with KKLT or, well, I'm not going to get into the details related to this perfect square structure. So if you don't know this literature or you don't know the topic, don't worry. I mean, you're not going to need this kind of things for the talk. So, okay, let's get started. Well, let's talk about the branes. We know branes very well in string theory, and well, what we know, well, possible interpretation, quite useful one, is that they are solitonic solutions in supergravity theories that, well, they break spontaneously half of the supersymmetries, and therefore, well, there's going to be some associated Goldstinos that I'll talk about very soon. But there's an alternative way of looking at branes, and this is the alternative of taking branes as some hypersurface in superspace. So for a very simple case of the M2 brane, for example, this we can use this interpretation in order to build the M2 brane action. So basically we consider the M2 brane as a three-dimensional hypersurface in well, a superspace with 11 dimensions that are bosonic. So this ZM has 11 dimensions that are bosonic, and then we have 32 dimensions that are going to be Grassmann coordinates that we parameterize with these theta coordinates. Okay, so based well, using this idea, Bershuf and collaborators, they built the M2 brane action that we're going to be using in this talk, and it has this aspect here. So it's, well, it's very similar to the bosonic one, but basically instead of having the regular metric, we have a metric, well, a metric superfield that depends on all superspace coordinates, and the same goes for the free form that we have in M theory. Well, this is the Wessumino part, of course. So basically, well, we can write this using index notation, okay? So we see that the metric, basically, well, it comes with a pullback, and we build the metric using the super VLY, as you can see here, well, the pullback of the super VLY, okay? And the Wessumino part, we have the three form that, well, the three form superfield that again we build using the, well, the super VLY pullback, okay? And also this three form superfield. And well, I will not be using, the indices are not going to be very important for the talk, but when you see like, indices like M, N, or whatever, these are referring to, well, space-time coordinates or superspace coordinates instead. And if you have indices like, capital A is going to be tangent space, so it can either be again bosonic, so it goes from 0 to 1, or it can be fermionic again, and it goes again from 1 to 32. Okay, so we have this perspective of branes being hypersurfaces in some superspace. And well, with this picture in mind, let's go back to what I said before. Well, from the bulk perspective, if I have a brane, and I'm going to consider branes that have, well, in asymptotically flat backgrounds. So this breaks half of the supercharges spontaneously. And as I said, there's going to be a series of gaussinos associated to it. And this will appear as fermionic degrees of freedom on the brane, of course. And then we have the perspective from the brane world volume, where basically we build the action of the brane. And I mean, before I was talking about M2-branes, but this works for any Dp-brane as well. So what we did is to build the action of this brane using a product of off-shell superfields. So we have the off-shell super Vielbein, the off-shell three-form, and so on and so forth. And if you remember, well, a product of superfields is a superfield itself. So what we have is basically that the brane action, it's a superfield, okay? And of course, well, because we took, well, we're considering superfields that are off-shell, then the brane action is going to have a theta expansion, okay, that will go up to order 32. Good. So now we put the background on shell, okay? This means we consider a solution with a brane, we break half of the supercharges, and therefore there's going to be half of the thetas that are generated by those supercharges that are spontaneously broken, that they will, well, they no longer correspond to, let's say, they don't correspond, if you want, to coordinates in the superspace that's left over, okay? So these are going to be, if you want, the gaussinos, okay? And these are going to be the fermionic degrees of freedom that we have on the brane. So, well, we said that we're using, well, we're building the action of the brane using the superfields. So half of the thetas that we have there are going to be fermionic degrees of freedom on the brane. Now, what happens with the other half? Because we're using these off-shell superfields, and therefore we have all of the thetas will appear in the action. And basically, well, the other half are going to be redundancies, okay? So what this is telling us is that there's going to be a fermionic well, gauge symmetry, and this is, well, kappa symmetry that we know very well. And indeed, for the M2-brane case, for example, Bershuf and collaborators, again, they showed that the M2-brane action is kappa symmetric. And again, this extends to all brane cases. So, well, kappa symmetry basically tells us that we can take these variations on the action, so we can shift all, well, the Grassmann coordinates by this quantity here, and kappa is a 32 component Majorana fermion. And basically the projector tells you that, well, by using this, you can switch off half of the Grassmann coordinates, okay? So now that we have an interpretation of what the fermions are, fermions on branes, what they are, we see that what we need is basically to obtain, well, the theta expansion of the brane actions, okay? So let me skip this. And yeah, we want the theta expansion of a brane action. And let's start by considering first the case of the M2-brane. So this is going to be the most simple case, and we'll start with that. And what we want is to obtain the theta expansion of this superfield. So in general, this is a very complicated thing to do, just obtaining the theta expansion of a certain superfield. But sometimes it's possible to do it. And I'm going to give you, well, just a rough idea of how you can do this. This is some technique that is based, well, it's called the normal coordinate system method. And well, I mean, it's been built by several people. I mean, initially people that were not thinking of superspace, but then it was extended also to the superspace case. And basically it's a method that allows you to get a Taylor expansion that tells you what the dependence of your superfield is going to be at a certain point in superspace. So what's the idea behind this approach? Well, basically there's going to be some special point where you have a lot of information. In our case, we want to make a theta expansion. So we want to make a Taylor expansion in theta coordinates. And the privileged place where we have a lot of information is theta equals to 0. So this is the origin of Grassmann coordinates. This is spacetime. Okay. So in order to take, I want to make a Taylor expansion because after all, a theta expansion is a Taylor expansion. And in order to do that, what I'm going to do is to consider that I have a geodesic, okay, that's crossing this hypersurface, theta equals to 0. And this geodesic is going to have, the parameter in the geodesic is going to take the value t equals 0 at theta equals 0. And then in some generic point that it's at theta different from 0, it will take t equals 1. And this is the point where we want to obtain the theta expansion, the value of the theta expansion of any superfield. So, okay. As I said, well, this has to be geodesic, and that's very important. I want a geodesic that has a tangent vector at this point, okay, at theta equals to 0, that's pointing only in Grassmann coordinates. So there's no coordinate in bosonic directions, but this vector is uniquely pointing in Grassmann coordinates. Okay, now I can do a Taylor expansion, but I do a Taylor expansion in the parameter t that it's parameterized in my geodesic. Okay, and I want to obtain the value at t equals 1 for this superfield. So, well, I obtain a typical Taylor expansion, and I see that basically these variations of my superfield with respect to the parameter t can be written in terms of Lie derivatives. So, the approach to obtain the theta expansion of any superfield is basically to iteratively act with a Lie derivative. A Lie derivative with the vector E being this one here. Okay, so that's the normal coordinate method, and by doing this, you can obtain the theta expansion, the theta expansions that we will need in order to construct the action. This slide is quite technical, and actually I don't have much time, so you're going to allow me to skip the details of how you proceed with this normal coordinate method. Okay. I mean, I can talk afterwards if someone's interested, but let me just, explain, for example, what happens in the case of the super Vielbein. And we're going to use the super Vielbein expansion a lot. So let me show you, for example, the first terms that you obtain from the super Vielbein expansion. So, I mean, the super Vielbein is this object here, okay? It's an object that actually, well, it involves the Vielbein, it involves the Gravitino, but then it has a theta expansion, and, well, of course, higher order terms are going to be more complicated. So the theta expansion, for example, for the component with lower index in space-time, okay, so bosonic if you want index, and upper index also bosonic, it has at order 0 the Vielbein, and then at order 1 you get a term that involves both our theta coordinate as well as the Gravitino. Okay, and of course, well, you can obtain higher order terms, or for example, well, you can consider the super Vielbein expansion with one index on space-time coordinates, bosonic one, and then for the tangent space index, you can take a fermionic one, and this gives you an expansion that has, for example, the Gravitino at order 0, and then at order 1, you get what's called the super covariant derivative. Okay, this is the guy that actually appears in the supersymmetry variation of the Gravitino. It's a combination of covariant derivative and fluxes that will appear quite a lot in the calculations that I'll show you afterwards. So, I mean, we have a method to obtain these theta expansions, in principle, to any order. And one last thing that we need to do is to consider, well, we're going to be considering bosonic backgrounds. And what this means is basically that all the terms that, when we perform the expansion that we want, eventually all the terms that involve the Gravitino, we can turn them to 0. Okay, so we have a technique to obtain, well, the theta expansion of any brane action if you want. So you could do this if you want in type 2A, in type 2B, or 11-dimensional supergravity. But the smartest strategy is going to be to start with 11-dimensional supergravity and start considering the superfields that appear in the M2 brane action. Okay, so if you remember, this is the M2 brane action. We built the action using the super Vielbein, okay? the supervillain appears here as well, and the 3-form superfield. Now, why do we want to do this first in 11-dimensional supergravity, and then, well, we will do dimensional reduction and T-duality? Why is the case? Well, first of all, in 11-dimensional supergravity, well, you have less fields, and then this makes things way easier. It's more, well, calculations are going to be more clean, and therefore it's going to be easier to find any sort of structure in the action. And well, the second reason is that actually in the theta expansion of the N2 brane, well, we said we have the super vielbein, okay, it appears in both places, and we have this 3-form, but it turns out that this combination here, when you consider the order, its theta expansion at order theta 1, you can see that from that order on, so higher orders than theta, well, than linear in theta, basically they only depend on the expansion of the super vielbein. Okay, so what this means is basically that if you know the theta expansion of the super vielbein in 11 dimensions, then already you know the theta expansion of the N2 brane action, well, of the N2 brane action. And the good thing is that at least the first terms, well, up to order 4 actually, of the super vielbein expansion, they were computed in a paper by Grisaro and Nutt. Well, they were partially computed by Grisaro and Nutt. So let's start playing this game. Okay, let's start computing the N2 brane action to order 2. So you can take the approach that I told you before. You can use the normal coordinate expansion, obtain the theta expansion of the super vielbeins up to order 2. And with those, you compute the metric, you compute this 3-form, okay? You compute the corresponding expansions, okay? So you have, you have the product of superfields, so you make the expansion of those superfields. And what you see is precisely that you can write the action, well, in terms of these combinations of fields. So let me just write the action in this shorthand notation, okay? So it's very similar to what I have here, but here I have the whole superfields, okay? Now what I have is going to be a combination of the metric superfield and the 3-point superfield, but this time, for example, I'm going to be computing the action at order 2, okay? And the superfields that appear here are actually, well, I use a different notation because they're actually truncated superfields. So if I want the action at order 2, for example, what I need to compute is the expansion of these superfields to order 2 in theta, okay? And what I see is that, for example, the metric superfield at order 0 has the metric, of course, and then at order 2, it has a fermion bilinear that has this aspect here. So it has, well, the Grassmann coordinates, some gamma matrix, and the super covariant derivative that, as I told you, appears in the supersymmetry variation of the gravitino. Okay, so, and it's a truncation both in fermionic order, so I truncated at order theta square, and also I took well, I told you before that I'm going to consider bosonic backgrounds, so therefore I already set to 0 all terms involved in the gravitino. So in a very compact way, you can just write the action as you see here with this superfield metric, so metric superfield, and this 3-form superfield, okay? And you can just perform the Taylor expansion using these expressions, and from there you read off what the brane action is going to be at order 2 in fermions. Actually, if you compute this, you obtain the same result that well, it was obtained, for example, in some papers by Marolf, Martucci, and Silva. But well, in that case, the approach that they took, it was not based on superspace, as I'm telling you, it was more like a brute force approach. And well, therefore, I mean, these papers, they serve us as well, some confirmation of the approach that I was proposing. So, okay, from now on, what I'm going to do is not so much, I mean, I will not be talking about brane actions as, that much, but basically because, well, I can obtain the brane action from the superfield expansion, I will care more about the superfield expansions from this point on. Okay, so this is what we had at order 2 for the N2 brane. Let's make things slightly more complicated. So now I'm going to go to order 4, and the brane action is going to look exactly the same. Is this guy here. But now my superfields, I need to get an expansion of my superfields that goes to order 4. Okay, and the superfield expansion at order 4 in the M2 brane case has this aspect here. So we see that again, we have the metric order 0, order 2 terms, okay, and then we have terms that are order 4 in theta. So we have some terms again that come with a super covariant derivative. So far so good. But then we also obtain a bunch of terms, okay, both for the metric and for the 3 form that are more ugly. So these terms, I mean, they have this aspect here. They involve, well, commutators of super covariant derivatives or super covariant derivatives and flux field strength. And therefore, well, it just tells you that the expression gets more and more involved as you go to higher orders. So, I mean, this is the expression that we obtained. And with these expressions, we can move on and we can start considering what happens with the T2-branes. Okay, so now let's change a bit the perspective. So we know that, well, I mean, when we have M2-branes and we have them in 11-dimensional supergravity, we compactify, we obtain type 2a string theory. And these M2-branes, they become T2-branes if they are not wrapping the M-theory circle. Now, this is what happens if you want for the bosonic M2-brane and D2-brane. But now I'm interested in, well, preserving the fermionic structure in the action. And therefore, I'm going to consider, well, this picture that I was telling you about before. And this is that, well, an M2-brane, it's, well, a hypersurface that is living in this superspace here, whereas a D2-brane is also a 3-dimensional hypersurface that lives in another superspace. So how do we relate them? Well, I mean, it's very simple, right? We just need to do a superspace compactification. So this, I think, it's a new idea. So let's first do very quickly what, well, the bosonic case, how it works in the bosonic case. So if I have in theory 11-dimensional supergravity, the ansatz that I'm going to take for the metric, for example, is going to be the following. So I have the composition of the 11-dimensional metric into the 10-dimensional metric, the dilaton, and the Ramon-Ramon one-form potential. And also I need to make an ansatz for the 3-form in 11-dimensional supergravity that decomposes into the Ramon-Ramon 3-form potential and the Nebel-Schwarz 2-form potential. So using this, you can go to the brane action. Okay, so this was the brane action that you had before. You can you can write this action in terms of your 10-dimensional fields. Okay, when you do that, you see that you obtain a bunch of terms. Actually, you find this combination very often where you have basically the pullback of the 1-form together with this partial derivative of the 10th dimension that tells you, hey, I know that, you know, there's a circle up there. That's the M-theory circle. So in order to get rid of this guy, what you need to do is to add a Lagrange multiplier. That's this term here. And the Lagrange multiplier, it involves both P, I mean, this guy here, this combination, and what will become the work volume flux. So, okay, you put these guys together, you compute the equation of motion for P in order to integrate it out, you solve for P and you plug it back into the action. And by doing that, you obtain the D2-brane action that has this aspect, as we all know. Okay, we have the D2-brane action. Now, what happens if you want to do it at the superfield level? Well, I mean, the only thing that you need to do is basically go from having fields all over the place to having superfields. So that's what you need to do. Instead, you can just follow the same approach. So initially we had the 11-dimensional metric superfield, and the same with the 3-form. Now you're going to make an ansatz for these superfields, and you're going to decompose them into 10-dimensional superfields. So the composition is exactly the same. And basically what I'm doing is taking every field in 10 dimensions and just saying that actually this is going to be a superfield. And everything is exactly analogous. Okay, now I have the brane action. It looks like this. And if I want to take a Taylor expansion, well, a theta expansion of the brane action, what I need is actually the theta expansion of the metric, of the B field, 3 form, 1 form, and so on. So how do I obtain these guys? Well, let's do it at the order fermion squared level. So what I'm going to do is to consider the ansatz that I had. So let's do a very simple case. For example, I said that the 10-10 component of the 11-dimensional metric is going to be this dilaton, this exponential of the dilaton, okay? And this is a statement that holds at the superfield level, and now I'm going to make a Taylor expansion in fermionic orders. So, well, I make the expansion of this dilaton, so this is dilaton, the bosonic dilaton, but then it will have a fermionic expansion, and now I'm interested in obtaining the term that has a fermion bilinear, okay? So let me make a Taylor expansion on both sides, okay? Here I have the bosonic metric, okay, the usual one. Same here, I have the dilaton, the bosonic term, and then I have a fermion bilinear, okay? So this is the fermion bilinear that appears in the 11-dimensional metric that has this aspect here. Whereas for the dilaton, I have this rho, which is some fermion bilinear, and I don't know how it looks like. And actually, the goal is to learn how this fermion bilinear looks like. So now I have the Taylor expansion. I need to identify things order by order in fermions. So basically, I can read off what the aspect of this rho is going to be. And well, basically, it's going to be this term here. But the problem is that, okay, I have a guy, a fermion bilinear, that has a lot of 11-dimensional superfields. So, I mean, this is the 11-dimensional supercovariant derivative. And what you need to do is to make a dimensional reduction of this fermion bilinear. In order to do that, I mean, well, I'm going to omit all the technicalities, but, well, you have, for example, the supercovariant derivative in 10 dimensions. So in order to make a dimensional reduction of this guy, you need to perform the dimensional reduction of the 11D gravitino, okay? And when you do that, what you find is that, well, this 10th component of the supercovariant derivative is given by the dilaton, the chirality matrix in 10 dimensions, and this operator delta that appears in the dilatino variation. And then, well, these 11-dimensional thetas, the Grassmann coordinates that they had in 11 dimensions, their dimensional reduction will require a scaling with a dilaton, and then splitting this, this fermion, the Majorana fermion, into its Majorana components. So just by using this, you can perform the dimensional reduction of this fermion bilinear, okay? And by doing that, what you do is you obtain an expression for this rho that was initially an unknown fermion bilinear. So basically, by doing this Taylor expansion and this identification, what you do is to you can learn, for example, what's going to be the Taylor expansion of the dilaton superfield in 10 dimensions. So you can play the same game for all the superfields that appear in the D2-brane action, okay? So you have all these 5 superfields, okay? And basically, you see that the expansion of the superfields has this aspect here. And again, when you do this, you compute the brane action at order fermion squared, and you see that the results are in full agreement with the results that were computed by Maros, Martucci, and Silva using some brute force approach. Okay, so actually, let me tell you that, I mean, at order theta squared, it's possible to do things at, using brute force, but actually, if you don't use the structure that we are proposing, it's pretty much impossible to obtain things at order theta 4. So, that's, if you want, the power of our approach. So, okay, that's theta 2. For theta 4, we computed the terms. I'm not going to give you the formulas because, well, in the N2-brane orders, terms at theta 4 were quite ugly. You can imagine that after performing a dimensional reduction, things are getting more complicated. But yeah, so let's keep it simple in that aspect. But what we did is to compute the T2-brane expansion to order 4. So the superfield expansion at order 4. So what's missing is T-duality. And because I don't have much time, I'm going to be quite schematic here. So before, what I did was to go from the N2 brane to the D2 brane by performing a dimensional reduction of superspace. So this was simply an extension of the typical bosonic dimensional reduction. Now what I'm going to do is, well, I have a D2 brane action and I want to obtain the action for any Dp brane. So in order to do that, usually what I could do is just take a bunch of T-dualities and, well, go from p equals to 2 to p to, well, any number. Now what I'm going to do, again, I'm going to extend this to superspace. So I'm going to make a bunch of T-dualities, but at the superspace level. So what's the approach? The approach is pretty much the same that we had when we did the dimensional reduction. Basically, we're going to start with some bosonic T-duality relations, okay? We're going to promote these relations to the superfield level, okay? Then when you do this promotion, you need to, well, you take the relationships, you need to make Taylor expansions, okay? And you need to identify terms order by order in fermions, okay? And finally, you need to use, well, the T-duality rules that relate fermions in both theories. And these are given by, well, they were given by Hassan in order to translate the fermion bilinears in type 2a to fermion bilinears in type 2b, okay? So as I told you, what you need to do is to promote the bosonic T-duality relations. So these are the bosonic T-duality relations, but now they're going to hold also at this level, at the superfield level. And well, I'm going to, I mean, there's nothing new that we can learn apart from what we did before. So, I mean, the approach is pretty much the same. As I told you, you can just make a Taylor expansion, identify the terms that are at order fermion squared, like here and here. And then using the Hassan rules, you can translate a fermion bilinear, for example, in type 2a to a fermion bilinear in type 2b. And that's what needs to be done. So I'm going to stop here. Well, basically, let me tell you what the outcome is of doing these T-dualities. So, well, not surprisingly, in the Nebel-Schwarz sector, basically the superfield expansion, both in type 2a and in type 2b, looks exactly the same. But in the Ramon-Ramon sector, well, you have different gauge potentials, and therefore, well, it needs to be computed case by case. Okay, and well, by doing that, basically you can obtain the brane action for any Dp brane at any fermionic order in principle. But as I told you, well, higher order in fermions become very, very complicated. Already at order 4 is actually a mess. And yeah, what one needs to do is basically to take this action, take the superfields that you have there, make the expansion to the order that you need, and just perform a Taylor expansion of this action. And that's it. So let me just leave you, well, summary of what I've been telling you, and thank you for your attention.
Great, thanks, Andre. While we wait for questions in the chat, so you motivated this by saying that you wanted to kind of understand this perfect square business a bit better.
Yes.
Do you now, or
can you still see my slides, or
I cannot?
Not anymore. Okay, maybe I can share the screen. So that's it. So thing is, yeah, I do have this motivation, but now you can see the slides, right?
Mm-hmm. Yeah.
Yeah. Okay. So point is, I mean, why do I want to understand this thing? Basically, I mean, the perfect square comes from the following fact. It's an observation that goes back to this paper by Dine, Ron, Cyber, and Witten. It tells you that if you have any supergravity theory where you have, well, gauginos and you can have some gaugino condensate, well, there's going to be this sort of perfect square structure, as you say, in the action. Now, this happens when your gauginos live on the same dimensionality as your theory, but so they are codimension 0 if you want. But as soon as you go to codimension 1, I mean, this is something that's demanded by supersymmetry, okay? But when you go to codimension 1, like in our Java Witten or codimension 2, and as in KKLT, it really is not clear what happens. So we know that supersymmetry is a very powerful symmetry, and definitely, I mean, it's going to impose some structure, but we don't really know how this is happening in these cases. So basically, by understanding the brane action, I mean, it's possible, let's put it this way. So it's possible, for example, to compute in the D9 brane case, okay? You can compute what happens in the D9 brane. You will have K-genus that in the D9 basically are codimension 0, okay? This is, well, if you want, you are in type 1 theory. And over there, you can see what, well, you're going to find a perfect square structure. Okay, so this is something that supersymmetry is telling you that has to be there. Very good. And now the question could be, what happens when you have an object like well, any other Dp-brane that is not a D9 brane? What happens with these other terms? Because the perfect square structure, again, I mean, it appears when you have codimension 0 object, but I don't really know what's going to happen, like, you know, how this thing is going to be manifest when I have codimension 1 or codimension 2 objects. And this is what happens in KKLT, for example. So this is why I want to compute the fermionic expansion on the branes.
Yeah, and does it work out to be a perfect square? I mean, it seems like going to the theta 4, you can
well, so let's say that what we're doing is a first step to answer this question. Mm-hmm. What you need to do is basically, so you need to compute the action at order 4 for Dp-branes. You need to fix the gauge for kappa symmetry. Okay, this is something that we didn't do. So it's, I mean, this is enough of a mess for now. So you need to fix the gauge. By doing that, you need to identify how the perfect square arises in the D9 branes. Okay. And afterwards, you can see what happens in the case of D7 branes, for example. That's the case of interest for KKLT. So the answer is basically, I don't know. I mean, we know what we need to do in order to answer that question, but well, it's quite demanding. We're not there yet.
Cool. Well, if there are no other questions, let us end here and thank Andre for his very nice talk with our emojis.